Dear students, up till now in semiconductor electronics, we have seen what is an atomic structure, and then from atomic structure, we saw what was valence electrons, then we saw what was a conduction electrons, then we saw the difference between insulator, a conductor, and semiconductors. Then we are concentrated on semiconductor, and in semiconductor we saw two types. One was a pure semiconductor, which was called as intrinsic semiconductor, and one is impure. When you add the impairing material, when you add, it is called as doping process. When you add the impure to the pure semiconductor, it becomes extrinsic semiconductor, and depending upon what impurity we are going to add, we are going to get p-type semiconductor and n-type semiconductor. So up till here we have seen. Now today we will see what will happen when we join this p-type semiconductor material and n-type semiconductor material together. Okay, now this concept gives rise to what is p-n junction. P-n junction will be nothing but a p-type material joined with n-type material. Now what happens in that, we will see. So here is a topic: formation of p-n junction, that is p-type material and n-type material you are going to join, and the interfacing part of it where the join is there, it is called as junction. So it is called as p-n junction. Now basically, if you see the definition of what is p-n junction, in a simple language we can say that if a p-type and an n-type material are brought close to each other, both of them join to form a junction. So you can see here, if you have a p-type material, say this is p-type semiconductor, okay, and if you are having a n-type semiconductor, this is n-type semiconductor. When you join this p-type semiconductor and n-type semiconductor, there forms a junction here. This is the interfacing part of both the materials. This is a junction, and this arrangement is called as p-n junction. So this is your p-n junction. Okay, p-n junction. Now here is the actual junction what we have shown. Okay, so if a p-type semiconductor is joined with n-type semiconductor, a p-n junction is formed. This is a statement in a easy language, in a simple language, what is p-n junction. Okay, we are not going to speak here about fabrication and the wafers and the growing and all those things. Okay, so we are just saying that it is a joint of p-type semiconductor with n-type semiconductor. We are not using any difficult terms like we have a semiconductor wafer, a thin p-type semiconductor wafer, and in that we are going to grow a n-type of semiconductor, and then we are going to form a p and n type of material, and then we will have a junction. All that are technical points we will not speak here. We'll just speak a simple language and say that a p-n junction is one where a p-type and n-type material are brought close to each other. Both of them join to form a junction. Now after this, what happens when you join p-type and n-type semiconductor? That is important. Now here you can see this is a diagram shown of p-type and n-type semiconductor. So here you can see this is your p-type semiconductor, this is p, and this is n-type semiconductor shown. Now in p-type semiconductor, we have majority charge carriers. As you remember, when you added the trivalent impurity to the pure semiconductor like silicon or germanium, we obtained or we got the p-type semiconductor. And in p-type semiconductor, the holes were majority charge carriers. So here whatever is shown in this yellow round, these are holes, these are majority charge carriers in p-type semiconductor. Okay, in p-type semiconductor, holes are majority charge carriers. So these are holes, these are your majority charge carriers. These are more in number because of the process of doping, and they are called as majority charge carriers in p-type semiconductor. This happens in your p-type. Now same in p-type, we also have minority charge carriers, that is some free electrons are broken from their covalent bonds because of increase in temperature, because of the temperature, we have a few electrons. So here one electron we have shown, and here one electron we have shown. A few electrons are there which are minority charge carriers. These are electrons which are minority charge carriers. Minority charge carriers. Now this is the explanation of the structure of p-type semiconductor. So in p-type semiconductor, we have majority charge carriers which will help you to make the current flow. The majority charge carriers are holes, and minority charge carriers, because of thermal effect, some minority charge carriers you get, and those are electrons. Now majority charge carriers are there because of doping process. You are adding impurity, so you are getting majority charge carriers. So there are many. If you add a small amount of impurity to the pure semiconductor also, you will get a large amount of majority charge carriers. Okay, so majority charge carriers are more. So they are more in numbers. That is why they are called as majority charge carriers. So in p-type semiconductor, you have holes as more in numbers, so majority charge carriers, and electrons which are obtained because of thermal effect. They are minority charge carriers. They are less in number. Similarly, if you see the n-type semiconductor here, in n-type semiconductor, you can see these electrons. There are many electrons because a pentavalent impurity is added to the pure semiconductor, and you are going to get many free electrons. So here electrons are majority charge carriers. These are majority charge carriers. And similarly, here also, because of thermal covalent bond breaking, you get a smaller number of holes. So here you can see we have shown one hole, here we have shown another hole. Less number of holes are present in n-type semiconductor. So here the holes become minority charge carriers. Holes become minority charge carriers. Okay. Now here is what we have seen, the structures of p and n type of material. And in p type of material, we are going to simply say that the majority charge carriers are holes and minority charge carriers are electrons, whereas in n-type semiconductor, the majority charge carriers are electrons and minority charge carriers are holes. Okay, now p-type is more of holes, and holes are considered as positive charges, whereas n-type is having more of electrons, and electrons are negative charges. Okay, now this is what a basic theory you should know when you are going to join a p-type semiconductor with n-type semiconductor. Now here what happens is, as we know, electrons are negative charge carriers and holes we are going to assume as positive charge carriers. So obviously when you join such p and n type of material, obviously the electrons, which are negatively charged particles, are going to get attracted towards the p side where there are holes which are positive charge particles. Okay, so here you can see these electrons will start moving to the p-type semiconductor. These electrons will start moving to the p-type semiconductor. Okay, now this is the, you can simply say that a negative charge particle is been attracted towards the assumed positive charge. Okay, similarly we can also see that the holes which are positive charge will be attracted towards the negative charge particles here. So holes from p side will start traveling to the n side. So this is something called as diffusion. The electrons from n side semiconductor are going to get diffused. They are going to be attracted. They are going to move towards p-type semiconductor, and the holes from p-type semiconductor are going to get diffused or moved into the n-type semiconductor. So this gives a concept of diffusion. So here we are going to make use of what is diffusion and what is diffusion current. Okay, now this is what is diffusion take place. Then we will see what happens when this movement goes on, and after some time what happens. So here we will first say that when p and n type semiconductor materials are joined, the electrons from n type semiconductor diffuse into p type semiconductor and combines with holes. So here what we are saying is, we will just speak about now electrons in n type and what happens with them. Okay, so here if you show the diagram, so the diagrams will be seen like this. Say this is your PN junction. This is your PN junction. Now here, this is your P-type material. This is N-type material. In P-type material, you have holes as majority charge carriers. We can show holes as majority charge carriers. And in N-type, we show electrons as majority charge carriers. Electrons as majority charge carriers. And now we are going to only say that the electrons from N-type semiconductor diffuse into P-type semiconductor. So this is the first step what we have seen earlier also. So these electrons will diffuse into P-type semiconductor and combines with holes. So this negative charge electron will move into the P-type semiconductor, and that movement is called as diffusion, and there it will go and combine with this positive charge particle hole. Clear? This is the first movement what you can start with the explanation of this majority charge carriers movement, that is electrons will go into P-type semiconductor and holes from P-type semiconductor will move or diffuse into the N-type semiconductor. So in this, the first step what we're telling is the electrons from the N-type semiconductor will diffuse into P-type semiconductor and combines with holes. Then what happens? So when an electron diffuses from N-type material to P-type material, it leaves behind an ionized donor on N side. Now what is this ionized donor on N side? This ionized donor is a positive charge and it is immobile. It is not going to move as your majority charge carriers movement, as it is bonded to the surrounding atoms. Now what does this all mean? Okay, so this also you can show with the help of a diagram here. So here you can see we will have a P-type and N-type semiconductor as we have told earlier. So here you can have your P-type semiconductor, N-type semiconductor. P-type semiconductor is having holes as majority charge carriers, and N-type semiconductor is having electrons as majority charge carriers. And as we said in the first step, the electrons which are negative charge particle will be attracted and they get diffused. They move into P-type semiconductor and combine with holes with. Now this is what we have told in the first step. Now in the second step, what we are saying is when this electron moves from N to P-type semiconductor, when this electron moves from P to N-type semiconductor, now this electron place is empty. This electron place is empty. Okay, now this becomes a empty place which is positive charged, and this is a ion. This is a ion. Now this becomes an ion, so you can consider this as a ion, a positive charge ion, because your negative electron charge particle has moved now, and the absent place of electron you are going to take it as a positive ion. Okay, now this positive ion is not a charge carrier. Is not a charge carrier. It is a positive charge, but it is not going to carry, it is not going to move. Okay, it is an ion which is a positive charge, but it is not going to move. Okay, so it is not going to carry your current. It is immobile, it is not going to move. So these are immobiles, ions. So like this, electrons will go, that many ions you are going to form here near the junction. Okay, so electrons from N side, when they move to the P side, the remaining place, the absent place of that charge carrier which is moved will become an ion, and the ion will be of opposite polarity and it is immobile. So negative charge electron is moving. The absent place of that electron is formed as a positive charge, which is an ion, which is immobile. Okay, so it is not going to move. These are the ions which are not going to move. These are the ions which are not going to move. Okay, this is the second step what you have to know. Then the third step, we will speak about the holes from P-type material, what will happen. So again, we will consider the same diagram. You can have a P-type and N-type semiconductor. Okay, so here you can have, this is P-type semiconductor, this is N-type semiconductor. In P-type you have holes as majority charge carriers, and electrons as minority charge carriers. Now in this third step, we are saying that the holes from p-type material diffuse into n-type material. It leaves behind an ionized acceptor, that is negative charge, which is immobile. Now a similar process is happening here also. Now this positive charge holes will move to the n-type semiconductor. They will be attracted by the negative electrons in the n-type semiconductor, and when these holes move, this place becomes vacant, and those will become an opposite polarity immobile charge. So they are not charge carriers which can carry the current, they will be immobile charge. Okay, so here when the holes go there, the vacant place becomes a opposite polarity, that is minus ion, which is immobile. It is not going to move, and many such ions will get concentrated as the holes are going to move into the n-type region. Okay, so here what we are seeing, the negative ions are getting formed at the p-type region, and similarly earlier we saw when the electrons went from n side to p side, positive ions were formed at the n-type region. Okay, so this is what we have seen. These were the immobile charges what were formed, which were ions. Okay, so these were immobile charges what were ions, which are not going to move, and they will also see that the main charge carriers from either side will also stop moving further. Clear? Now this is a process which is going when you going to join p and n type of semiconductor. Now these two layers of positive and negative ions forms depletion region. Okay, so here we come to a concept of what is depletion region. So again, if you draw the same type of p-n junction structure, you can see that when you join p-type material with n-type material, okay, in p-type you have holes as majority charge carriers, and in n-type you have electrons as majority charge carriers. Now we have told that in step number 1, 2, 3 that electrons from the n side will diffuse into the p-type semiconductor, and holes from the p-type will diffuse into the n-type semiconductor, and the absent places of this majority charge carriers will become ions which are immobile. So in n-type semiconductor we will get positive polarity, that is if electrons are negative then you will get positive ions here, and in n-type where holes are positive charge carriers we will get negative ions here. So this is a positive and negative ions which are immobile, they are not going to move. Now this area will be reducing the majority charge carriers. The majority charge carriers, that is the holes in p-type and electrons and in n-type, will be reduced here, it will be depleted here. So this region will be called as depletion region. Okay, so here you can see this area where there are only ions which are immobile, there are no holes and electrons. So this area is depleted of majority charge carriers. Therefore this region is called as depletion region. This is called as depletion region. This is one of the term what you have to remember when you join a p-type and n-type semiconductor. The term depletion refers that the region near the junction is depleted of their respective majority charge carriers. That means majority charge carriers of p-type semiconductor was holes, majority charge carriers of n-type semiconductor was electrons. So those majority charge carriers are not seen at the junction because of this formation of these ions. So that area at the junction is depleted. It has been reduced of the majority charge carriers. There are only ions there. Okay. Now here you can see the depletion region, whatever we have told earlier. Now this is your p-type semiconductor shown here. These are holes which are majority charge carriers in p-type semiconductor. Similarly, you can see electrons which are majority charge carriers in n-type semiconductor. So when electrons move into the p-type semiconductor, that is called as diffusion, and when holes move into the n-type semiconductor, that is also called as diffusion. We get the absent places of those charge carriers as ions, and we see that positive ions are formed in the n-type semiconductor near the junction, and negative ions are formed in the p-type semiconductor near the junction, and this area is called as depletion region. So this is the situation formed, that is called as depletion region, formation of depletion region. Now this depletion region is now not allowing the majority charge carriers to move. So what diffusion was taking place, that is the movement of electrons from n-type semiconductor to p-type semiconductor, and the movement of holes from p-type semiconductor to n-type semiconductor, that movement, that diffusion, okay, which was more in the beginning, will now reduce. That means we can say that the diffusion current, that is the movement of charge carriers, is called as current only. Diffusion current, what was taking place when we joined the p and n type of semiconductor, which was more at the beginning, now it will slowly reduce, because there is a field now here. There are ions, immobile ions, which are formed, which is a depletion region, and these ions will be acting as an electric field. So here you can see you have positive ions and negative ions. So here you can consider this positive ions and negative ions. Now this part you can consider as a voltage, as a potential difference, as an electric field. Okay, you can consider this as an electric field, and you can say that this electric field is negative here and positive here. So some kind of electric field is developed here because of this negative ions and positive ions, and this is one which is going to oppose the movement of holes to n side and electrons to p side. So it is going to oppose. So it is going to somehow oppose the diffusion, and it is going to stop the diffusion. Okay, so here you can see the same concept we have told. These holes will experience a repulsive force from the positive ions, which prevents further diffusion of holes in n-type material, and repulsive force due to this negative ions will prevent the electrons further diffusing from p-type material to these electrons from n-type material to into pp-type material. Okay, so the same concept again we have shown in diagram. Okay, so that is where the electric field of the ions is going to take place. Now as the region acts as barrier, okay, so whatever we have shown at the depletion region, it will act as a barrier, that is opposite electric field. Okay, the electric field will oppose the movement of majority charge carriers. So as this region acts as a barrier between p and n type of material, this is also called as barrier junction. This is also called as barrier junction. So here whatever we have shown earlier, p-type material and n-type material, now we will concentrate at the junction. So at the junction we showed that here were negative ions, and here were positive ions, and these were not allowing the majority charge carriers electrons to diffuse into p-type, and holes from p-type to diffuse into n-type. So they have a barrier now. There is a barrier, there is an obstruction, and this is called as a depletion region. It is a barrier between p-type and n-type material. It is also called as barrier junction. So there occurs a potential difference. As I've told you earlier, there occurs a potential difference here. This is a potential difference, positive, negative and positive. So this is a potential difference. You can take it as VD. This will be potential difference here due to the formation of ions across the junction, which is also called as potential barrier. Okay, so here we are having this region named as depletion region. We are having this region named as depletion region, and in the depletion region, whatever that electric field we have, it will be having a potential difference due to the formation of ions, and that will be called as potential barrier, or it is also called as barrier potential. Okay, anyway, this potential, this electric field is going to oppose the movement of majority charge carriers from p to n and n to p. Okay, so this barrier is going to prevent further movement of holes and electrons through the junction. That means it is going to stop the diffusion. Okay, now here you can see the diffusion will stop because of the barrier potential, but there is one more concept which will come into picture, that is drift. Now drift is going to be because of the minority charge carriers. Now here in p-type semiconductor, we see that you have holes as majority charge carriers and you have electrons as minority charge carriers. Electrons as minority charge carriers. Similarly, in n-type, we will be having holes as minority charge carriers. Now we will not speak about majority charge carriers because majority charge carriers movement from n to p and p to n, which was called as diffusion, has stopped because of the potential barrier. Because of these ions here, the majority charge carrier movement has stopped. Okay, now this was your negative and positive electric field, or the potential difference, you can call it. Now this electric field will see that the negative polarity here of this electric field, these negative ions, will see that these minority charge carriers can travel. They will give them the repulsive force to travel. Similarly, this positive potential can see that this minority holes can travel across the junction. So this is called as drift. This is called as drift. This moment of minority charge carriers will be called as drift. Now the majority charge carrier diffusion has stopped and the minority charge carrier drift has started. Okay. Now this drift will take place for some time because of the potential difference or the electric field whatever is developed, because in the depletion region for some time this drift current will flow, and one stage will come when both the diffusion and drift will be equal to each other and there will be no movement of any carriers, whether it is majority or minority carriers, and there will be an equilibrium. The net moment will be zero, and that is when we say the p-n junction is formed. That is when we say the p-n junction is formed. Clear? So here, what is diffusion current? As I told you earlier, it is the moment of the majority charge carriers of p-type and n-type semiconductor. So here the diffusion current can be defined as the flow of charge carriers, majority charge carriers within a semiconductor traveling from higher concentration region to lower concentration region. This is nothing but whenever you have a simple p-n junction, whatever you have in p-type semiconductor, you have holes as majority charge carriers, and in n-type you have electrons as majority charge carriers. When electrons move because of the concentration, because they are negative charge particle, they will be attracted towards the positive charges, that is p-type, and this positive holes will be attracted to the negative side. Now this movement of majority charge carriers will be called as diffusion, and this movement is called as diffusion current. Then what is drift current? Then again we will be seeing the p and n type of junction, and now we will consider the minority charge carriers. So this is p type and n type, and here we have already formed the depletion region after we join. So here you can see the negative ions, here you can see the positive ions. Okay, now this depletion area, this potential, this voltage will not allow the majority charge carriers holes to move to n side and electrons from n side to move to p side. Now the electrons which were there in minority as minority charge carriers in p type, they will be supported by this negative positive polarity to move, and even holes which were minority in n side, that will also move because of this positive ions here. So that is acting as a repulsive force, so they start moving, and the moment of that is called as drift current. So drift current can be defined as the charge carriers moves in a semiconductor because of the electric field which is developed at the potential difference. That is a depletion region. Whatever electric field is developed, that electric field will make this charge carriers to move. So initially diffusion current is large and drift current is small. So when we join the p and n junction, as the diffusion process continues, the space charge region on either side of the junction extend, that is the depletion region in between at the junction will extend, thus increasing the electric field strength and hence drift current. Drift current will increase as the electric field is increasing. This process continues until the diffusion current equals to drift current, thus p-n junction is formed. In a p-n junction under equilibrium, there is no net current. So the concepts of diffusion and drift, that movement of charge carriers, majority charge carriers and the drift charge carriers, both will stop, and there will be a no movement of charge carriers. The net current when the formation of p-n junction is done, now after some time, the net current, the net movement of charge carriers will become zero, and there is no movement of charge carriers. Okay. Now this is a state when you are forming the p-n junction. Now here you can see the last stage of p-n junction is formed now. Now this is your p-type material, this is n-type material. You can see here this is p-type material. So this is p-type material, this is n-type material. Diffusion has stopped, drift has stopped, and the p-n junction has been formed. This p-n junction is nothing but it is a semiconductor diode. This is a semiconductor diode. p-n junction is taken as semiconductor diode, and the symbol of this diode is shown like this. This is an arrow here. This is an arrow where you're going to consider the terminal of the p-type semiconductor, and there is a bar here which is going to be considered as a terminal of n-type semiconductor. So the terminal of p-type semiconductor is taken as anode. So here also you can see this is anode, and the terminal of n-type semiconductor is taken as cathode. So here also you can see cathode. And now henceforth we will be representing this p-n junction as a basic semiconductor diode structure. Okay, and the diode arrow you can see it is showing you the flow of positive carriers, that is the conventional current. The holes from p-type, they are going to move to n-type semiconductor. So it is a positive carrier movement, and that has been indicated by this arrow. Okay, so this is a arrow and this is a bar. So this is a symbol which is going to give you that is p-n junction formation, and it is nothing but a semiconductor diode. Now this diode, by using external electric field, can be forward bias and reverse bias. That we will see in our next part. Okay. So thank you, students.